Um, hmm? What? I just turned that on. Okay. So yeah, I am apparently Chip, but also I'm Manish. I work at Mozilla on Servo, and I've been using Rust for like 3 years now. Okay. Yeah. So so what is Rust? Rust is a new language that Mozilla is developing to fill a void that has existed in the programming world for a very long time now. Traditionally, you have two kinds of languages. Before the talk, I mentioned these two kinds in a group. I didn't mention all languages, but I sort of grouped them. You have languages which give you access, which give you access to the internals of everything, but as a result are unsafe. These are extremely these are extremely fast, but these are also very easy to mess up. You forget something, you have you forget to check a pointer, and you have some segmentation fault somewhere. That segmentation fault could instead be a big security bug if you're not very careful. Um, and then you have languages where they're slow, but you never have to worry about this. You can have bugs, but you can't have scary security issues that ruin your day. So Rust asks the question, why do we have to choose? Why must we choose between having performance and having safety? Can't we have both? And the answer is yes, you can have both. Um, uh, like let's just quickly go through the issues with C++. Like you have C, this applies to C as well. With C++, you have um, issues like dangling pointers, iterator invalidation, thread safety issues. In in C++, a dangling pointer is simple. Like if you have a function and it has something created in its local scope, and you return the pointer to that object no longer exists. This function returns a pointer to an integer that may become garbage data once the function exits. In more complicated situations, that could be some vector or something, in which case you will have a segmentation fault or something very scary. Um, this is this is a very simple example, like really, but you can imagine this getting much more complicated. Slightly more involved example is iterator invalidation. Uh, can anyone tell me what's wrong with this example? Yeah. Reveal.js doesn't like zooming. Let's see. Aha, it does work. Okay. Okay. Yeah, no, it doesn't work now. Maybe I can. No, that doesn't work. So I'm creating a vector here, filling it up with some elements. Um, and then I create an iterator over the vector. I iterate over that iterator, and at each point, I push an element to the vector. So what's wrong here? There are many things wrong here. But okay, what will this code do? Yeah, it's an infinite loop, but it actually is not, because in it is an infinite loop, but in most cases this will segmentation fault, depending on your machine and depending on where this code lies. If there are other things going on, it will segmentation fault because of the ways vectors work. Does everyone know what the heap is? A rough idea? Like who doesn't? Okay, good. So you a vector is allocated on the heap. When I push a few elements to it, it is allocated. Like if I say a vector, I want a vector of size 4, it will create a vector of size 4 on the heap. Once I push more than 4 elements to it, it will be like, oh, I don't have enough space. It will allocate somewhere else on the heap, a place of size 8 or something, and it will copy these over and push the new element. Now the problem here is that this iterator is just a pointer to the element you're at right now. Or it looks all fancy, but it's just a pointer. And when I push this, if this vector reallocates, the original memory is reclaimed. So it's going to, so it'll go like 1, 2, 3, maybe it'll get to 2, and then the vector reallocates. Now the vector was here, and now it's being moved here. The pointers, the iterator still points here. So new vector is here, but now it moves next, and its segmentation faults. So this will just crash. Again, it depends on what's around the vector, but it'll give you all sorts of weird results. Now this is a much more subtler thing. It's very hard to prevent this kind of thing from happening in C++ quite often, and it's very hard to notice that it's happening. Another issue is, of course, thread safety. When you have multiple threads, they're all running in parallel or something, and you need to be very careful about making sure that you only access one thing at a time. And enforcing this is a manual job. All of these things I've mentioned, I mean, all of these things, you don't actually write C++ code like this. You're not supposed to. But how do you enforce it that that never happens? There's always a way to do it manually. You can always avoid it. But once you have a huge code base, what will you do? So this is a problem. This is why is it a problem? You get segmentation faults everywhere. You want to avoid such runtime failures. You can't always avoid runtime failures, but it's good to be able to avoid them when you can. This is a big source of security bugs. We have all sorts of issues these days caused by memory safety. Heartbleed is caused by something similar. I'm not necessarily saying Rust would solve heartbleed, but it's a memory safety issue, and it means that memory safety is something we should care about. The existing solutions for safety are usually like using something like a GC, a garbage collector. Java uses this, JavaScript, Python, Ruby, they all have some form of garbage collector. The garbage collector carefully keeps track of all of the data that you put on the heap, and it only cleans it up when it knows that no one is accessing it. This means that you have this little daemon running in your code, running in your program, keeping track of everything, scanning, looking for things, cleaning up. This has a cost. This has a runtime cost. Every time you do this, it's going to take time. You have GC pauses, which mean that like if you suddenly there's too much stuff on the garbage collector is like, wait, it'll stop the rest of the code and it'll just spend like half a minute cleaning everything up. This happens, you can actually notice these in browsers sometimes, where if you do a lot of JavaScript and it then slows down a lot of things for quite a bit. Yeah. Has anyone played Minecraft and just exploded tons of TNT all over the place? Do you know how slow it gets when you do that? I'm not sure, but that's probably due to garbage collection, because that's probably creating a whole bunch of things and then just deleting them at the same time. Just the XKCD about seg faults. Many of you might have seen this. So yeah. Now all of these problems, Rust tries to solve them, and to most extent it does. We have Rust. What Rust has realized that these things can be checked for snap. You can check for all of this at compile time, as long as you design your programming language in such a particular way, and you write your code in a particular way. It's very liberating to write code in Rust. At the same time, because what Rust is, whereas in C++ you had the compiler not doing anything and you had to take care of it yourself, and in Java or whatever you have the runtime taking care of it. In Rust you have the compiler taking care of it and yelling at you when you mess it up, and that is the core benefit here. You now don't need to think about this. You can let the compiler think about this. After a few months or weeks of programming in Rust, eventually you learn to think about this subconsciously, and the compiler stops yelling at you, but basically now you're able to write good code. And that's something that was hard previously. Just like because you guys wanted to know this, the reason like Mozilla is using Rust to build Servo, which is a research and experimental browser written in Rust. The idea is that our current Firefox is old, more than that, more than that. It's like 15, I guess. It's old. It's a code base that's very old. All the other browsers are actually pretty old now. Chrome is newish, but it's based on older code base, and there are lots of things that were not done at that time. Like at that time, you didn't have that many cores on your machine, so parallelism using threads was not a thing. And now you have these 8 core, 16 core machines, whatever, and browsers just don't use that. They use threads, but they don't really use them where they can use make the most of them. And part of the reason is that there is where it takes a really long time. Firefox recently released the multiprocess version. That thing had been in development for 5 years, and it took that long because you can't just make a whole code base thread safe with a snap of your finger. You have or process safe. You need to do that bit by bit. The idea is that we will write a new browser. It will be highly parallel. It will be in a language where parallelism is easy. In C++, parallelism is not easy. It's very easy to mess up. Right now, what I was working on when I came in here, I was debugging a segmentation fault caused by a thread safety issue. Right now, um, and the it's so you can have this new browser and research project. It lets us try new things. We have a whole bunch of things like web render, which uses the browser use the GPU as much as they could. Now we use it, and we have extremely fast rendering because of that. So there are many things we've tried out, and there are they're moving slowly. Move parts of these into Firefox. Already has latest Firefox right. It is running Rust um, soon, or well, not so soon, but over time, it may be running much more Rust code. We're already working on taking a lot of parts of server and putting it in Firefox. So that's basically why Mozilla is interested in it, and many people are interested in it for six reasons. Like you have so many fields, browsers are one of them, but so many fields of software which where performance is extremely important. So you have to write it in. Yeah, performance, latency, these things are important. You need your code to be fast. You need it to be memory efficient. And these have been traditionally written in C and C++ because there never was any choice. So the thing you had to do when you're working at these is just suck it up and hope your code is safe. There's really there are band-aids to the whole thing where you use a few tools, you use a few extensions, and hopefully it's slightly better. But this problem is completely solved. And so many people are interested in Rust for that. And like Rust is now being used for browsers. There are people writing operating systems in it. There are people doing web development with Rust. There are people doing embedded development. There are people just writing applications in Rust. Is everything. If you want, I can tell you like there's a whole page full of people who are using Rust for various things in production. I can show that later if you want. But yeah, so that's like it can be used anywhere you care about performance, and it can be also used anywhere you don't care about performance. If you're मिल रहा है free में तो ले ले मतलब so um, yeah, like one very common use of Rust is, and this is where C and C++ used to be used a lot, is if you have a Python code base or a JavaScript Node code base or some Ruby code base or whatever, and you need to do something that takes a lot of CPU time. You need that to be fast. There's a limit to how fast you can make Python, Ruby, JS code. Like, even a function call in Ruby has a significant cost. Um, whereas with Rust or C++, you have a very trivial cost for calling a function. So what you do is that you just write that part in Rust and then you have it call that. There's so many people using Rust like that. And one extra advantage is that, and we've heard this from many people, is that Rust teaches you systems programming. So systems programming is like when you're dealing with these low level things like working with pointers and all of that. So a lot of the people who are doing this have people who know how to program in Python or maybe JavaScript, but not C++. And now if they had to write it in C++, they would have to teach them, okay, be careful about this pointer, all of this. Rust doesn't let you mess these things up. So when you're writing, if you're writing Rust code, you automatically learn about all of these things. So yes, so like, that's basically why Rust is being used, how it can be used. I mean, there are almost all applications of C++. Rust is a very good fit. For applications of other languages, also it can also fit. You- Yeah, like that is what Firefox is doing right now. It's slowly taking parts of it and replacing them with Rust parts. Servo is not at a stage, and it will take a lot of time to get to a stage where it could be just another browser released next to Firefox. But at the same time, there are parts of it which are very good and very near complete. So you can take that, put it in Firefox, complete it. There, done. So a lot of people are just replacing slowly with Rust. Okay. Any questions so far? So okay, not plugins, but Rust can compile as a C library. So any language that lets you any language that lets you call C functions. Is that nice? That one? Yeah. Okay. So anything that lets you call C functions from another language, and almost every language or every language I know of has this. In Python, it's called C types, I think. Um, Anything that lets you call C functions, you can call Rust libraries as well. You just write your Rust library, and the final function you want to call, you mark it as a C function, and you can just call it. This is well documented if you want to learn about this later. Um, what else? It is a hell of an annoying language to program in, because the compiler, for the first few weeks when you're learning Rust, you'll be like, this compiler doesn't want me to compile anything at all. Because the I'll get to that in a second. So so it's trying to teach you a certain discipline about the code. Now, even if you're writing C++ for like 10 years and you know how to write C++ that's safe, the way Rust wants you to program might still be different. It's safe, but it doesn't mean that you write the code the same way. So like, not syntax is fine. The like the way you structure the code, the way if you want to do some task working with a hash map or something, you might do it differently in Rust, and you might structure your code differently, move things around differently. So learning this takes time, and until you get this right, the compiler will be yelling at you. The compiler also tries to be helpful. It's like, okay, you did this wrong, you should try this. There was this one incident when I touched this part of the Rust code base with, I had to work with some borrows and some very complicated, and all I did was I changed a few things. I tried compiling, copied the suggestion, tried compile it again, and I did that like 5 6 times. It was so I had to do it a few times, and then it just worked. And I knew that I knew that it was safe. If it were C++, I would have used a shared pointer or some other expensive, relatively expensive operation in that place. So, um, yeah. So, yes. So that's the drawback, is basically that there is a learning curve. I argue that that learning curve exists for C++ as well. It's just that for Rust, the learning curve is like this. You learn that borrow checker and all, and then after that it's easy. For C++, you will initially be writing, oh, this is all easy, and then you will hit seg faults, and as time passes, you'll be like, oh no, this is actually hard. Yeah, it's like this. Yeah. So you need, I mean, it gives you a false sense of security sometimes. And yes, there are ways of writing safe C++ code, but it takes time to learn that. So yeah, that's the drawback. What's your well? Rust. Does Scala have a notion of purity? Yes, right. Rust is not a pure language, so it will not. Pure languages are. It's a concept in functional programming where everything is basically immutable. So if you want to change something, You don't actually change it, you just create a new one. You want to append to a list, you create a new list and stuff like that. And it's a pretty neat concept, and it also avoids a lot of the problems here, but with safety. But many of these languages have to use garbage collectors and are still not as fast as C++. Rust doesn't have purity, but Rust has immutability by default, and um, Rust has most, like, what you would expect from a functional language. It has quite a few things, like it has things like iterators, generics, a good type system. It does not have a lot of things like you would see in Haskell, like higher kind of types or weird things like that. So it's not a completely a functional language. It was inspired by OCaml initially, and it has a lot of things that make it so that people who don't know functional programming can still program in it. It itself is not a functional program, a functional language. It is similar to many functional languages. So yeah, it yeah. In what? In like Android and stuff. Oh, there's an IDE plugin for Eclipse, I think, and for there's an one for IDEA as well. But I mean, for Android, there are libraries that let you. There's a library called Android RS something. I forgot. Sorry, I can find it. Look it up later. But there are libraries that make it easy to make APKs and link to Rust with NDK. Like so, yeah. So yeah, Rust lets you cross compile, and now it's made it very easy. Like if I want to cross compile to um, some ARM board, I just say rust up install something something ARM. I'd have to Google that string, but it's the Rust version and then the target spec for that, and it'll just get me everything I need to compile that. I need to have a linker as well for that toolchain, and then I can just cross compile to ARM. And the plugins and all, like if you want to use it in something like Android, again you can use C code in Android. So you do the same thing that you do for using C code in Android, and then just put Rust code there instead, and just compile that Rust code. Yeah. Um, okay. So I'll go ahead. कितना time बाकी है? Okay. So okay, I'll quickly go through like the just go through the basic look and feel of Rust, because I'm not actually going to teach the syntax. There are I'll link to these later, but there's a Rust book and many other places where you can get good Rust documentation online. So I suggest you learn these from there. I will try to explain the tricky bits, but I'll just quickly breeze through this part so you can. So we have ifs, loops, functions. Um, the It's a nice reversal from C where the parentheses around the ifs are not there. You can put them if you want, but the braces are mandatory, which is good because when you forget braces, there are problems. But if you forget those parentheses, it's actually not a big deal. So yeah, it's similar to Python that way, but it's not indentation aware. There is a, a little code a friend of mine wrote that lets you write Rust code as if it were Python, in the sense that it's still the same keywords and everything, but instead of braces, you use indentation and colons, which is cool. And the README says do not use this. So yeah, yes, okay, I'll get so that is a full type declaration. I'm saying that I let mut I32 equal to 0. So I'm saying that it let I is a mutable variable of type 32-bit integer. Let it be 0. Um, I don't need to specify the type usually. Rust has type inference, like Scala and many other languages. So if it can figure out the type, it will figure out the type. In this case, it would have figured it out that it's I32. Mut means mutable. If I want to change it, I say mut. If I don't say mut. So this could have just been let I equal to 0, but I'm trying to change it. Loop is an infinite loop. You have for loops, while loops as well. Uh, you can do break, if. You have functions that look like this. Um, yeah, this is a tricky bit, which people have sometimes have a hard time getting. Semicolons have meaning in Rust. It's not like semicolons are entirely necessary. It's not like they're unnecessary. They have meaning. Um, Normally, in most cases, they are necessary. Between two statements, this one needs to have a semicolon. But at the end of a block, the last one, depending on whether it has a semicolon or not, it means something different. I believe Ruby has something similar. Ruby doesn't use semicolons, but so for example, um, let a equal to, if b greater than 1, do some stuff, c, else 1. So this last value, whatever it is, evaluates to the value of this entire if block. So that's what a becomes. Similarly here, the greater than, if a greater than b, a else b. So you can nest these things, and so often you won't even see return in a function because it will just return like this. You just look at the last thing. These semicolons are necessary. This one, if you added a semicolon here, then it will have a type error because there is nothing being returned here. So then what is a if it comes here? We know what a is if it comes here. If it weren't there in both places, it will be fine. It's like, okay, there's no value on either side, so a is the unit type, which is just basically almost like void, sort of. Implicit, yeah. For return, yeah, you just type return. You need explicit return as well, right? So, but most cases you don't need explicit return, and like you can, again, you can also return from blocks. You can't say return, but you can evaluate entire blocks to a single value. So that's pretty tricky, but also very useful. It leads to some code looking nicer. Um, Instead of switch case, you have match. There is no fall through here. So you can have 0, 2 or 3, 4 to 7, 8 to 20, and then that's a wild card. You can also have like inside the match you can put more this thing, and note that again here this is a block. So if I put some number here and I put some number here, this entire block would evaluate to that number or some value or whatever. Yes, I'm getting to that. Yeah, but yes, it is exhaustive. If I omit this, it'll complain because it does not know what to do if the numbers are there. Now, I could obviously put that thing saying underscore do nothing. But and if you think about it, if this was not there, what would size be if the value was 21? So it needs to have something for that. So this must be there. This is very useful in that the way Rust handles null and other things, you are forced to deal with this. You are forced to deal with errors. You can bubble them up, or you can handle them, but you are forced to deal with them. Um, or you can even say crash when I get an error, but you are forced to explicitly handle everything. You have destructuring. This is like Python. You can say let a be equal to some pair, let b equal to ab, and it was swapped. Um, you can also like, so I can destructure and matches. Let smaller equal to match pair x comma y if x less than y. So if x is less, if so take pair is two numbers. Now in this case I didn't put numbers here, I put x and y. It's saying that if pair is something where the first element is any element, but let's call it x, the second element is any element, but let's call it y, and then if x less than y, it's x, and any element, let's not give it a name, and any element named y, let's call it y. So I can do stuff like this. Now here I'm just matching on 0. If it's at 0 0, it's the origin. If it's at 0 and any element, but let's call that y, it's here, and stuff like that. So you can so I'm destructuring basically. It's a structure of, it's a tuple with two elements. I destructured that, and you have regular structs. These are like classes, except classes you have to the functionality and the data is all in one place. Here you just say how the data looks. You can add the functionality later. This is just a struct. You have enums. Now these are not like any enums you've seen in any other languages. No, these are not like Java enums. These are not like C enums. These are not like C unions either. They're similar to C unions. Um, they are like Haskell algebraic data types, data, or they are the correct term for them might be tagged union. So what? So we have that struct point I defined before, with just x and y. So what is a shape? A shape is either, in this case, a circle or a rectangle. But what what does it what is it if it's a circle? Like a regular Java or C enum, you just say shape type, circle, rectangle. You don't have the actual information about the shape in that. So a shape is either a circle or a rectangle. If it is a circle, it contains a point and an integer, which is the radius. If it's a rectangle, it contains 2 points, the corners. Um, so this means that a value of this can either be a circle or a rectangle. And when it is a circle, it contains different things than when it's a rectangle. In C or in C++, you would use a union type and then an enum put together and use the enum to choose what to pick in the union type. There is also something called boost variant to do that. But in most well, in Haskell and in other functional languages, you have something similar, but most languages, you don't have something like this. So these are not regular enums. A real world example is, this is a nullable type. Rust does not have null. You cannot have a null type ever. Remember when I said that what would happen if this wasn't there? In many languages, that means that it's null. Rust does not understand what null is. What Rust has instead is option. If you have an option type, it is either a sum of that type or it's none of no type. So it's like this can be used to say null. But now this means that you explicitly acknowledge that this value may be null in its type signature. So I can say that if I have this point, I can create a circle shape. Now again, matching is exhaustive. Okay. So because matching is exhaustive, you are forced to handle cases that aren't there. Which means if I match on a shape, if it's a circle, I deal with it and I create the area. If it's a rectangle, I do this. If I omitted this line and it got to a rectangle, what would it do? It doesn't know. So it's like you must say what a rectangle is. Now, given that we handle nulls with option, and options and enum, and matches are exhaustive, you are forced to handle the null case always. You can explicitly say, no, I know that this isn't null, throw this away. But you have to explicitly say that. There are helper functions for this, but no, I know this is null. Crash if it's not, if it is, but you have to explicitly say it. Or you can, yeah. And the error handling also uses these, but I'm not going to get into that right now. You have generics, like you can have, many languages have these, like templates or generics in Java, where you say that a type can take another type. The type is actually a type when it's only a type when you give it another type. An option doesn't mean anything, but you can have an option of an integer or an option of a string or something. And the methods are implemented in a separate block called enable. You also have traits, but I'm not going to get into those now. It's one of the cooler parts of the type system, but yeah. This is where the tricky stuff happens. How is Rust memory safe? It comes from an observation that aliasing and mutability are a problem. By aliasing, I mean sharing. If multiple variables or multiple names, if there exist multiple names for the same thing, and someone is able to change it, the thing, then we have a problem. One example is the dangling pointer. You return the dangling pointer, and then that area is deleted. That's changed, but there's someone else looking at it. Similarly, iterator invalidation. In that example, there were two people looking at the same vector. One was the iterator and one was the variable for vector itself. Both were trying to modify. One was trying to read and one was writing to the vector. This caused an issue. If you should only be writing to something if you are the only one who can see it. Functional programming languages have noticed this, but they solve the problem by saying don't mutate. Rust is like, it's okay to change things as long as no one else can see that you're changing it. Because what happens is that in code, you have assumptions based on something not changing. You have a variable here, and in fact, thread safety is the same issue. Because you have some variable here, you expect it won't change till here. And if it does because of another thread, your host. So these core issue in all of these problems is that aliasing and mutation should never mix. And Rust memory safety design is around this. So first we have moving. This is simple. If you have a primitive type or something that only contains things, copyable types, like there aren't any pointers involved or there's no indirection, everything you see there is part of that thing on the stack. Then you can, if I say let x equal to 5 and let y equal to x, both y becomes a copy of x. This happens in most languages. Now if I say let x is a vector of 3 elements and let y equal to x, y is not a copy. Y is the same vector, but x no longer actually can be used. So I can now print y, but if I try to print x, it will give me an error. Okay. So moving is basically like one person giving the it's giving it to the next. Like now you own this. X owned the vector, now y owns the vector. Functions can also take ownership. So if I give a vector to the function has taken ownership. Hmm? Because there's it's a primitive type. So with primitive types and with there's a concept of a copyable type. A vector has indirection, it has a pointer, it's not copyable. Things without pointers, where you should be able to copy them without any memory safety issue arising, are copyable. We don't really have time, sir, otherwise I'd explain it more. I can explain it later if you want. So if I call this function, then after this I cannot use myvec. And what happens is that if you have ownership, you are responsible for cleaning up. So this function now has ownership of this myvec. It cleans up right here. It calls destructors, removes the heap allocation. There you explicitly say clone, which explicitly creates a copy. Now you have this concept of borrowing. On its own, moving actually solves the problem already, because there's no sharing an owner. Like you can either forbid mutation or you can forbid sharing. But you sort of want, that is not how people program. You can theoretically write your code like that, but you don't want to. So instead, you have this concept of borrowing. If I have a vector, I can say that let y is x, that y equal to and x. This borrows x. It's a temporary borrow. X is still the owner, but y is now allowed to look at it. Now x and y can both read from it. I can also create an explicit copy like you asked. Similarly, this function can now borrow vec. Now it no longer needs to clean it up here. It's been given it temporarily. It's been like, okay, I have something here, you can see it too. But I can, so it looks at it, it's done, I can still use it here. The thing with the borrowing is that it doesn't let you mutate. Like the third time I'm muting that. So if I have a vector and if this is borrowed, I cannot push to either x or y. I can't mutate it because it is borrowed. There are two people looking at it right now. Note that, by the way, this concept of borrow is completely compile time. There's nothing at the runtime saying, oh, this is borrowed, this is borrowed. The compiler says, okay, this is borrowed for this scope. No mutation here. Mutation's fine here. If y is a mutable borrow, then this is and mut. It's a new syntax. Now it means that y is allowed to read it, write to it, everything. But now x can do nothing. So if I have a thing, and I'm like, okay, here, this is yours, this is not yours, but here, take it, do what you want, give it back to me at the end of the day. Now now it's only with you, I can't see it, I can't change it. So it's fine for you to look at, change it or whatever, because it's not being shared. But you have to give it back. So you're not allowed to clean it up, but you can change it and then give it back. So here, y can change it. X cannot read or write to it because it actually does not have access right now. But then once this is over, X is able to write to it again. And right here, it'll be cleaned up. Yeah, okay. Forget that. And finally, Rust, all of these things are nice, but when you really need to get to the core of it, you sometimes need to use unsafe. If you want to write the vector struct, you want to design that, you need to deal with raw pointers. Pointers which don't care about borrows or ownership. So Rust gives you an escape hatch. Like when you want to write code like this, use unsafe. With unsafe, you get to use raw pointers and a few other cool features. You get to use them to the full extent, and there are a bunch of things you can do here. Again, there's not much time, but I can explain this more later. Now here I'm using unsafe code to actually do something unsafe. I'm doing something where I create a segfault. You're not supposed to use unsafe code like that. You're supposed to use unsafe code to write something which is safe, but Rust can't tell that it's safe. When you write unsafe code, you're saying, trust me, I know what I'm doing. I'm an engineer. So yeah. So this is basically a quick overview of Rust with some of the syntax, some of the tricky bits. Um, there are some more features. You have thread safety. It's a very cool system on its own. I can again explain it later if you want. You have a lot of zero cost abstractions like iterators and everything. You use tons of iterators. Your code becomes tiny, but yet it just compiles down to a for loop. You have error handling is done by result types, which is these are not exceptions. These are cooler. You have associated types, closures, plugins. You have all sorts of libraries. You have web development libraries, um, game development. There's a browser engine, parsing, all sorts of stuff. There's a site crates.io where you'll see all of these crates. These are some resources. I'll keep this up at the end of the thing. So the third from last point is these slides. The first two are some resources where you can learn Rust. Thank you. Any questions? Is there another thing after this? Okay. I mean, whatever. Rust has no runtime. Like if you think that C has no runtime, it has a tiny one. Rust also has no runtime. There's a tiny one. That you do at the OS level. You set a U limit. So Rust, like if you can do it in C, you can probably do it in Rust. Stuff like this, like setting a memory limit, whatever. You can do it by calling a C function that does this also. So you can always talk to the OS because Rust lets you call OS C function and stuff like that. Um, Rust is yeah. So Rust does not impose a memory limit aside from the memory limit that the OS imposes on it. Huh? Yeah. Okay. I guess time up. Yeah, just take this. Take off this. I don't have a shareable link right now.